Hi, everyone. It's really cool to be in this workshop discussing some of the latest work we're thinking about for robotic learning and training and benchmark. So the title of my talk is Simulations, Robots and Virtual Agents Towards Training and Benchmarking Human-Level Activities in Embodied AI. I wanted to start the talk by opening up our aperture a little bit, and then we're definitely going to focus on talking about benchmarking. So the world is changing really rapidly, and I'm showing you four so-called future applications of the related set of technology. Some of them are already here, be it virtual tutors or robotic home robots, or rescue and work assistive robots, or just this interface between physical and virtual world to bring humans experiences in AR, VR. So looking at these potential applications and the set of technologies that are empowering these applications, we're starting to see a very exciting trend is where the world of atoms and world of bits are starting to intertwine in unprecedented way. And in this, as the world of atoms and world of bits revolve each other and intertwine, we ask ourselves, what are the parallels? What are the important ingredients and technologies that needs to happen for these applications to take full shape? Well, I would say that there's quite a bit of parallel and interesting connectivity between these two worlds. In the world of atoms, as we know it, the most important form of intelligence is animal intelligence, especially human intelligence. We have a embodied shape, our body, and in the world of bits, we start to see a parallel story where we can imagine embodied AI as the software brain will empower, enable virtual agents and avatars in the virtual world. But the crossing is also extremely interesting, is that physical robots that operate in the world of atoms are more and more going to be empowered by embodied AI algorithms, whereas virtual agents in the form of digital twins, avatars, will have interactions, will be partially driven by humans. So this is just a thought, draft picture of what we see, where the human intelligence and embodied AI in the world of atoms and bits are starting to intertwine. But in order to really fulfill the application dreams, as well as create embodied AI that truly can work as brains for robots, as well as for virtual agents, there are still quite a few big challenges remained. This is by no means to be an exhaustive list. It's just a lot of conversations and discussions going on within Stanford with my collaborators. But some of the key questions that excite us are, for example, there is a need to develop photo and physical realistic environments to develop embodied AI as we think about the virtual world. There's a need right now and a lack of it for a set of potentially accepted tasks or environments or evaluation standards to train and benchmark embodied AI and robots eventually. We still are in very early days of algorithms that can perform ecologically complex and diverse, such as human level tasks. Everybody dream of dishwashing robot, but we're pretty far from that as far as I can see. We also have questions like, how do we generate and render the body, different bodies in embodied AI for virtual as well as physical agents? We also are just scratching the surface in terms of understanding the collaboration between agents, whether it's between virtual agents or virtual agents and humans and robots and humans in both virtual simulated and real world. So these are, again, just a partial list of big questions that continue to excite our research agenda. But today, we're here to mostly talk about training and benchmarking. And I think there is a huge opportunity in robotic learning and embodied AI to up the game here, because without that kind of challenges and a push for that kind of North Star, it's hard to make large strides of progress. Speaking of progress, let's just get back to reality a little bit. This is a fun video to watch of, when we are dreaming of all kinds of robots helping us to wash dishes and cook meals and clean toilets. By and large, today's robots are still struggling with extremely simple tasks in an environment, a natural environment like this one. So there's a long way to go. In our field, we are seeing a lot of really exciting work happening. Most of them are still, including our own labs, are focusing on skill level tasks and short horizon goals and punchier tasks that are not composed of multiple subtasks and goals. And we recognize that a lot of our own work and work from the field are published in relatively small scale and anecdotal evaluation setup. The tasks and the environments are experimenter picked and not very standardized, and there is no agreed upon metrics. So these are all the this is not a criticism, it's just where the progress is, and there is opportunity for pushing this forward, especially recognizing real world is very different. Real world is ecologically complex, it's dynamic and uncertain. It's largely, it has large variabilities, interactive and social, and extremely multitasking. So we recognize the moment because we have seen inspirations from related fields where benchmarks and data sets, and more importantly, tasks and goals help the many of the research effort to move forward, and we call that North Star questions for different fields. And maybe there is a opportunity for pushing this North Star question for robotic learning and embodied AI. And that's what we want to share with you today, is a new work that we're presenting here at CoRL'22, ecological robotic learning environment, and how it can enable our training and benchmarking on a large and diverse set of activities. And we call this behavior, which is benchmark for everyday household activities in virtual, interactive, and ecological environments. This is work done by a fairly large group of students and collaborators. Many of them are here at CoRL. I really encourage you to find the students and talk to them about this work. So before we start showing you what are the details of our benchmark and the environment, I actually want to step back and ask the question that is very important, is what do we want to make robots for? And this question is not only asking ourselves as researchers, the whole public, the society is asking us. There's more and more awareness of the relationship between technology and our civil society, our economy. There's a lot of concerns about replacement of not only human labor, but human agency and human dignity. So when we are when we started this project, it's actually really important for us that we take a human-centered approach for defining how we want robots to help us. So let me just run a test for you, right? I know I cannot see your hands, but let's pretend you're answering these questions, at least to yourself. What kind of activities would you like robots to help you with? And I think that answer might vary given who you are and your preference in life. But let's say, what about cleaning kitchen floors? Most people find cleaning work pretty tedious and tiring and don't mind some robotic help. Shoveling snow, is another very tedious and sometimes even dangerous task. Folding laundry gets a little bit interesting. Some people actually like it. I personally like it, but it is very boring and tedious and repetitive for many others. Cooking breakfast depends, right? Cooking breakfast for your loved ones might be very fun. What if you are a fantastic chef? So this might not be a task you want robots to help. What about opening Christmas gifts? We're about to do that. How many of you actually want a robot to open Christmas gifts for you? So maybe the answer is not too many. So the bottom line is, we want to focus on people. We're making robots or embodied AI agents to help people, not to replace people. So we took a large number of human household activities from different government data sets, and then we put together a user study of a fairly large number of people, 1,400 plus participants on Amazon Mechanical Turk. We try to diversify them as much as we could. And we asked the question, how much would you benefit if a robot did the following task for you? And the answers are really fascinating. There is a statistically varied, set of preferences. And we rank these answers, and we find some patterns, such as cleaning tasks are preferred by people to get robot help, whereas a lot of entertainment and socialization and, like opening Christmas gift or playing squash or are actually preferred by humans to do it themselves. And though, and here's just another way to visualize the different clusters of tasks. But the bottom line is, we looked at this result. We picked the top 1,000 activities where the scores are high for the need for robotic help. And we're about to share with you, we built this training environment and benchmark by focusing on these 1,000 tasks that respects humans' preference. Okay, so now we have the task. The real work is, how do we build a training environment and benchmark setup? We, after getting the task and defining the task, we need to actually get the environment. We put a strong focus on ecological and diverse scenes and objects. We want the scenes to look as realistic as possible. So we actually obtained digital versions of 50 real world environments across many different scene types, like homes, offices, restaurants, schools, and so on. And these are scanned scenes, and we built a 3D environment from this. And then we also obtained more than 5,000 3D object models across 30 plus different object properties, 1,200 plus object categories. This is still ongoing work, but it's important to diversify and have this large data set of interactive and realistic objects. Now we're ready to put together a simulation environment for this training playground and benchmark playground. Simulation environment has been a really important breakthrough, I would say, in our field. They have a lot of important properties that are very useful. They're fast for training. They are safe for robots and the people and the environment. And a lot of them, it is quite a reproducible way of doing science. And frankly, you can sample infinite number of possibilities in these training environment, simulation environments. So a lot of people have been making incredibly important and useful training simulation environments for robotic learning. And here we just acknowledge a small set of work, pioneering work in this, and our own work built upon and are very much inspired by these simulation work by other members of our community. In our behavior work, we collaborated with NVIDIA's Omniverse team and created a simulation environment called OmniGibson that focuses on realism in physics, perception, and interaction. Here's an example of physical realism of different effects such as thermal effects, lighting and reflection, fluid deformability, transparency. Here is a user test on the perceptual realism by asking users to score how realistic our environments look like. And behavior environments has scored fairly high compared to other environments in terms of this perceptual realism. And of course, we strive towards interactive realism, where I'm just showing you examples of our robots able to deal with rigid, non-rigid, and fluid objects. Here's just a table summarizing another important property of behavior, which is the diversity and complexity of the tasks, building upon these realistic scenes and objects and realistic renderings and physics. We focuses on the scale as well as the ecological complexity of our activities, and try to focus on long horizon tasks that are similar to what humans perform in everyday environments. So this is just the beginning. And one important question is, what do we do with this behavior simulation environment and benchmark? Well, we hope that we can develop next generation algorithms to empower virtual agents, embodied AI, and eventually robots. But the first step towards that is actually to understand how we are doing right now. And this is ongoing work. I'm just showing you a little bit of the early work in benchmarking is using two families of algorithm. One is the soft actor and critic RL algorithm. The other one is PPO-based algorithm to see how they're doing on behavior benchmark. We selected 3 long horizon tasks: store decoration, collecting trash, and clean tables, and have used a different setting for benchmarking. The first one is providing no privileged information to the robot agent. And frankly, the model more or less fails because there's no additional information, including action primitives, and the performance is at 0. Then we relax our condition a little bit and provide some action primitives, and we can see that our model can the PPO algorithm can leverage on the privileged information and show some signaling performance. If we add on top of action primitives some memories and extra privileged information, the model performance improves as well. This is only the beginning, and it's just a small scale experiment to show you that there is a long way to go in training robotic algorithms and embodied AI algorithms to perform these long horizon tasks. And of course, in this very complex environment, And of course, the eventual goal of many of us here at this conference working in robotic learning is the real world transfer. And while behavior focuses on simulation world, we are actually paying attention to study how these algorithms can transfer. We have built a small environment in our department that has a digital twin and a physical twin as a small apartment in our lab. And here's just a example of showing you our mobile manipulation robot called Marvin has successfully performed a sequence of tasks by picking up the bottle, and it will go towards the trash bin and navigate there and put the bottle in the trash bin. This is just a very small anecdotal example to show you the kind of work in sim to real environment we're working towards. There is also a lot of failures we are, not showing, and for example, failed to picking up the bottle. Just now it was failing to navigate to the right place. Failed to place the cup in the trash bin, and so on. So all this is saying we have a long way to go. So last but not least, I want to just finish this with a small promotional video to show you about behavior. Here you're seeing the diversity of the environments we are using, and here you're seeing the interactivity the robot, the simulation environment can enable. Here's more examples of objects. Notice the articulation and different properties. And we hope you also get to talk to our team members about this and check out our paper that's published. And last but not the least, I want to acknowledge our students and postdocs and collaborators on this project, as well as all the funding sources. Thank you so much.